Welcome all to the London Align workshop. This is the first time we're hosting a Align workshop in London, but hopefully not the last. As someone who was born and somewhat raised in London, moved down to the southwest earlier, it's great to be back here and have an event here. So today I want to share some thoughts I have about the importance of taking an engineering approach to AI safety. And this is something that has informed my own research and the strategy of FAR.AI quite a bit, but it's not something that I've previously actually explicitly articulated. And I'm excited to share it with this group because I think that this is a really great audience to critically engage with this. So I suspect that there's going to be around equal parts people thinking that this idea is too unambitious, but it's not giving a high enough level of assurance that AI is surely going to kill us if we only have the level of standard that you would have in civil engineering or another discipline. And then another third are going to say the opposite reaction, that this is far too ambitious. Like, we can't possibly do this with AI systems. It's far too complex, messy. And then maybe a third of people are going to agree with me, but that's boring. So I'm here for the debate. All right, so I want to start by saying what is the goal that we're trying to solve here. So what I'd posit is we want to get to a point where we have a standard, a technical standard for AI that, if we followed, would produce a safe AI system with a high degree of confidence, not certainty, but let's say that there's greater than 99% chance that this is going to work. And just having a standard is great, but it's not enough. We also need to have universal adoption. And so in order to get that universal adoption, I would posit that we need to have broad buy-in from the scientific community, from AI companies, from governments. Otherwise, we're just not going to be able to get that degree of coordination. So this needs to be something that's quite legible and has substantial evidence behind it and isn't too costly as well. So that's what we'd like to get in. Let's look at where we are today. So I was at the Indian AI Impact Summit a few weeks ago, and if you if you were hoping we might have some grown-up behavior from AI company CEOs that just work together, have a grown-up conversation, you maybe need a different plan. So that's sort of one outcome, and then let's look at a conversation with Demis and Dario at Davos. That was just back in January.
But I think the other issue is the geopolitical competition. There's obviously competition between the companies, but also US and China primarily. So unless there's an international cooperation or understanding around this, which I think would be good actually in terms of things like minimum safety standards for deployment. I think Dario would agree on that as well. I think it's vitally needed. This technology is going to be cross-border. It's going to affect everyone. It's going to affect all of humanity. Actually, Contact is one of my favorite films as well. So it's sort of funny enough, I didn't realize it was yours too, Dario. But I think those kind of things need to be worked through, and if we can, maybe it would be good to have a bit of a slightly slower pace than we're currently predicting, even my timelines, so that we can get this right societally. But that would require some coordination. That is,
I prefer your timelines.
Yes.
So this is a little bit more encouraging, maybe. But I think it's very interesting that we're starting to see AI company CEOs openly talk about how they would like things to be going a bit slower than they are, and that they want to perhaps do that, but they have challenges coordinating. In the case of Dario, it's concerns around China. Now, we're not going to solve all of geopolitical coordination in this conversation, but what I want to hone in on is why it's been so hard to get coordination on this topic. And I would say that the focus of a lot of this room is that we don't know how to build safe AI. And that's true, and that's a problem. But I think it's actually even worse that if we did build safe AI, we wouldn't know if we'd succeeded. And if we'd built unsafe AI, we wouldn't know if we'd failed, potentially. And if we had some kind of crystal ball that tells us, is this next training run going to be misaligned or aligned? But I think we probably could get AI company CEOs, governments around the world to say, well, we're not going to deploy the unsafe thing, and we will deploy the safe thing. So obviously getting to that level of prediction about the future is challenging. That's what makes AI safety hard. But I think that we can get something that's almost as good. And so what I think we should really be focusing on as a community is developing a standard for safe AI that meets these three criteria. The first is, maybe the key one, assurance. If something meets the standard, it's actually safe with a high level of probability. Again, not certainty, but it's very likely safe. But that's not enough. It also needs to be auditable. So it might be very difficult to make a system that complies with the standard, but once you have complied, it should be easy for a third party to be able to verify that so that people don't cheat on it effectively. And then I think the last part is maybe the one that we often kind of forget, and maybe I expect to get the most pushback on it, but it needs to be efficient. We can't be making overly onerous requirements on developers. So we should be requiring the minimal set of properties to provide a high level of assurance. And this could still potentially be quite costly, right? If you think of something like a nuclear reactor, it is just much more expensive to build a nuclear power plant than it is to pile a bunch of uranium on top of each other until it reaches criticality. But part of the design goal is that you have containment, that otherwise it's not a useful product. So if building safe AI turns out to be very hard, then this could still impose significant costs, but it shouldn't be imposing unnecessary costs. Otherwise, people just are not going to adopt it and follow it. So I think that's a good North Star to have. What I'd like to propose as an approach to developing such a standard is to take an engineering style approach, to have a design that is perhaps inspired by some theoretical understanding, but ultimately rests a lot on rules of thumb, a lot of empirical testing, and then building a lot of safety factors, safety margin into your design so that even if you're wrong about certain things, the outcome isn't catastrophic. And I want to contrast this with a lot of the AI safety field, I think, takes a more scientific approach, right? So things like mechanistic interpretability are trying to fully understand, reverse engineer a system so we can make really rigorous predictions about it. And that's great if we can succeed at that. And I think it's useful to try, but I'm trying to focus on something a little bit more pragmatic here that we could develop in the next 1 to 2 years and really hone in the next 5 to 10. I think for some other area that people are often inspired by is more mathematics. So formal verification, rigorous proofs, things like guaranteed safe AI are in this territory. Again, great if we can do it, but I wouldn't say we've managed to build complex engineering artifacts that are fully formally verified. I'll have these kinds of guarantees, even if we're able to do small parts of it, like nuclear reactors will often have a formally verified control system, but you've not formally verified the whole thing. So what does that actually look like concretely? The first property that I would recommend we try to design towards is modularity. And I think this is one where a lot of people probably think, okay, that's crazy. Like deep learning systems, the defining characteristic is they're not modular. It's like a big monolithic neural network. And I certainly don't think we're going to be able to test neural networks layer by layer, let's say. But I think that we already have a lot of modules in our systems, despite not having explicitly designed for that. So we have teams of AI agents operating. Each of those agents is a module. You've obviously got the scaffolding that goes along with it, but you can put various kinds of control measures in place. And even the neural network itself has areas that are a little bit more modular. So you've got different checkpoints, and it's interesting and relevant to test both the foundation model and the post-train model. They're going to have different properties. It might be easier to test a foundation model in certain ways. So I think we can still leverage modularity that we do have, and we could try and design more of it in our systems. And I think a good concrete example of this is that developers are starting to implement these layered defense pipelines. And this is for misuse right now, but I think you could imagine something very similar being used as an AI control mechanism. So this schematic, which actually is a pretty good reflection of what Opus 4 did, but every model is a little bit different, is user queries first go to an input filter, which is a specialized model. Usually it's a reasoning model, decides whether this is a safe thing to respond to or not. Then you've got the main generative model that has its own, safety training. And then you have an output filter, which is another specialized model, usually one with a classifier head. And the reason I want to hone in on this is that we can test each of these components for input filter, the main model, of output filter separately, determine their attack success rate individually, determine the correlation, and then compute an end-to-end attack success rate. But surprisingly and confusingly to me, people just don't seem to do this. Like, I've not seen people evaluate these systems in that kind of modular fashion. And I think it's really sort of missing a trick, because you can both get an estimate of the mean time to failure that is much lower than you could establish by end-to-end testing. Like, if you test each of these components for 100 hours and you only find one failure rate and they're independent, well, you multiply it together, you get something that's basically 100,000 hours. You're not going to be able to probably spend 100,000 hours. You only had to spend 300 hours to get that estimate. That's great. In practice, things won't be independent, but you can still get a much better estimate. But you also can get just a qualitative sense of how much safety factor you have here. Like, if you can break 2 out of 3 of the components pretty easily, but one of them is really hard, but you don't have much defense in depth, it's very likely that some new attack would succeed. And then you can also do things that are more like destructive testing, where you put a system into a situation that's much worse than it would be in deployments, and maybe you give an attacker white box access. And if you don't find an attack even under that setting, then again, you can be more confident that you'd be robust to some completely new threat model. But again, people just don't seem to be doing this very much. And I think this is a missed opportunity. So the other property, which again, fairly basic, but I don't see people mostly doing, is make predictions about the safety properties of your system. So I think an example of this would be, if you're doing a lot of post-training, predict how much more reliant your model is going to be when it's trained on twice as much human data or has more RL time steps. If you're worried about reward hacking, predict how that's going to evolve as you do more post-training with RL with a verified reward. Safety scaling laws are a good example of this. And crucially, this is not trying to have a unified theory. We're not really trying to explain what's going on here. We're just trying to make a prediction that's going to hold in some local region. And then if that prediction holds over time, but now we have an empirically validated rule of thumb that we can use to help us design the next set of systems. And I think a good example of this is we had some work a couple of years back looking at the offense-defense balance in adversarial robustness. And what we found is that if you double the amount of compute used for adversarial training, then this basically doubles the amount of compute requirements of a number of queries an attacker needs to break your model. And the nice thing about this is that if you say, well, I want to be robust to an attacker that has a $1,000 compute budget, then you can compute exactly how much you're going to have to spend to be robust to this. And obviously, this isn't a hard law of the universe. It might break down, but you can give yourself some safety factor, and especially combined with a modular defense, you can get to a point where you're actually pretty confident, and you can get more confidence over time if you deploy these systems and indeed your predictions hold true. But again, I don't mostly see people making these kinds of predictions. And the final property, which probably sounds like the most obvious and vacuous of all of them, is actually test if your system is safe. And I think the thing that's confusing to me is we mostly just don't do this right now. I mean, we have very detailed model cards from a lot of the developers, which is great, but they're mostly focusing on dangerous capability evaluation. And that's important, but we're getting to a point where, well, these models have dangerous capabilities. So are they safe or not? Okay, we're not really testing for that in much detail. So I think good examples of this would be red teaming, whether that's for misuse or AI control measures. Another good example would be people have started doing testing for evaluation awareness, which could undermine the whole regime, deception, scheming. But I think generally we need to be building out actual kind of alignment evaluations. And I think there's lots of reasons to be, worried about that. It's hard to have a rigorous alignment evaluation of a model's evaluation aware, but there are mechanisms we could use to get a pretty high degree of confidence. We can make very realistic tests. We can train probes to detect if a model is eval aware and try and ablate it. This is something that we need to be building out, because I don't think people are just going to stop building models just because they possess potentially dangerous capabilities if they were misaligned. And I think a encouraging instance of this is some of my colleagues recently trained probes to detect deception, and the nice thing is that they found that they generalize to completely new areas. So we trained on a reasonably diverse data set, things like true false questions, sycophancy, open-ended conversations, but nothing to do with programming or coding. And then we evaluated on programming problems, and it just generalizes really quite well. It very cleanly separates the distribution of deceptive answers with just hard code results to the unit test versus the mainline solutions that are actually attempting to solve the problem. Now, not perfect. We've also found some cases where it doesn't generalize, but the point is this is a tractable empirical problem. We can come up with better solutions over time. So I think the key takeaways for me from this is that right now, cooperation on AI safety, whether it's between companies or between nation states, I think is held back by just not being a clear standard for what makes the system safe that we can rally around. So it's very hard to say, is a particular developer cutting corners on safety or not, because there's just no there's no consensus on what you should even be doing. And in order to be a good coordinating standard, a safety standard needs to both be reliable in the sense that it's providing a high level of assurance. If you actually follow the system, it probably is going to be safe. It needs to be auditable so that third parties can test it. You're not just relying on trust. And it needs to be efficient. It's not making overly onerous, costly demands. It's going to cause people to really try to avoid implementing the standard. And I believe that engineering safety can deliver on this for a combination of modularity, testing components one by one, establishing those safety properties, predictions, and to develop empirically validated rules of thumb, and then end-to-end safety testing as a kind of last line of defense. But I imagine there's going to be a lot of people who may disagree with this. That's fine. That's great. I'd love to engage in that conversation. I'd love people to talk to one another, but I'd really make a case that we should be trying to find some kind of safety standard, even if it's not this. Come up with your own approach. Okay, so in a rare turn of events, I actually ended before time. So I think there is time for some questions, pushback, comments disguised as a question about the engineering safety approach, if anyone has them. Otherwise, we can also move to our next speaker. Yeah.
Biggest question I have is having a standard seems great.
Yeah.
How concerned are you about multiple competing standards, meaning we get no standard?
Well, yeah, I mean, that's the great thing about standards is how many there are, right? Well, I think that maybe we need a standard for standards. I'd say having multiple competing standards, if they're all good standards, maybe that's fine, right? I think it's not a big deal of China has an electrical code, the US has an electrical code that different. I think we're still better off than if neither country had an electrical code and things just, wires caught fire in buildings now and again. A certain degree of customization is not a problem. I think where it's an issue is, well, we've seen this already actually with misuse, where you've got to have a threat model for who the attacker is, and different developers have chosen mutually exclusive threat models, and all of them are kind of reasonable. They're are targeting a real set of threat actors out there in the world. But because they've targeted a different set, what happens is that Claude refuses your request, well, ChatGPT will probably answer it and vice versa. So that's not really giving you much protection. So there are cases where if it's more of a security consideration, where it's only as secure as the weakest link, you need kind of coordination to make sure you cover something rather than not this kind of patchwork approach. And I think the other issue is if there's kind of a race to the bottom on standards and people just comply with the least rigorous standard. But I think I said the standard of standards idea is a joke, but I think there's something there where if you have a meta standard that's more like companies have liability, but you can have a safe harbor if you follow a standard that adequately addresses that risk, and then it's found that you had some failure and another standard out there would have addressed this risk, but the standard you implemented didn't, well, that removes the incentive to kind of choose the weakest standard. But yeah, I think it's a challenge. I don't have a perfect answer to that, but I think it'd be good for us to at least start thinking about how to operationalize these things. I think
All the suggestions you made seem very reasonable, also sort of obvious. And then the next question, probably the people in the companies also figured some of these, yet we aren't doing them yet. So it seems like maybe this isn't the bottleneck. So the question is like, what do you think are the actual bottlenecks here? What's the theory of impact? Why haven't we already started doing this 5 years ago? And will it work this time?
Yeah. Well, maybe Rohan, who's up next, can also address some of this. Like, why aren't people doing this? I think, yeah, it is kind of obvious, but Transformers is obvious as well. I do think there is a certain degree of just the culture and general approach in machine learning has been you have one benchmark and you're optimizing end to end to hit that benchmark, and people just aren't thinking about it from an engineering approach as much. I mean, most of the AI safety community, I think, has been approaching it from more of a, I think they've been trying to shoot for something more ambitious than this and been missing the mark. So I do think there's genuinely a thing where like people haven't been trying to do this, and that's why it's not happened. Not all of this requires AI companies to do. Like a lot of this you can just do yourself. Like we've published safety scaling laws. Like we were not a frontier developer. You don't need to be that. But yeah, I think that to actually engage with that question, I would say that a lot of the time there's not an incentive to really critically examine your own system. And a lot of the time, if you actually take this kind of approach, you'd say, oh yeah, our system fails to meet basic safety guarantees, right? Like I was saying, oh, you red team each component for 1 in 100 hours and you only find one vulnerability. I don't know, in many cases you just say, oh, the input filter doesn't run on images, it only runs on text. Okay, that took us 30 minutes to break. That's a real life system that is used by billions of users. I won't say which model it is, but it's deployed. And so I think that's part of it where people aren't trying to do this sort of more rigorous evaluation approach because they know it's not needed by not meeting those criteria. Yeah. All right.
Hi. When proposing these standards, do you have in mind something like what Miles Brundage is proposing, which is this: we should have an institution that is like an auditor, and this auditor has these standards that ensures that are met in every company? Or are you thinking more like culturally we should all do this, or do you even have something else in mind? Pragmatically, what are you thinking about?
Yeah, no, it's a good question. Yeah. So I would say that this approach is somewhat agnostic to how it's enforced, right? So this could be something that's like SOC 2, it's an industry standard. Maybe you need it for insurance requirements, but like no government is saying you have to be SOC 2 compliant. This could be something that's more like the code of practice, which is, it is voluntary. You can choose to sign it or not, but it is ultimately like a way in which you can be compliant with a piece of regulation. I would say that we probably want to start with this being more of a tacit industry standard. So think like, IETF, not building codes, and get some experience with it. But eventually, if there are things that are clearly, working and required to build systems that are safe, then yeah, it should be translated into regulation. But I wouldn't start with that. I think we both don't know what those properties are in many cases, and it will make it harder to get buy-in and traction.